In this video, I take a very basic RBD destruction scene that was already set up in the previous Destruction for Beginners video and build upon that project to demonstrate how to generate higher detail noise in the interior of each fractured geometry piece and apply optimizations by packing the geometry and delay, load, and swap techniques to improve cooking performance. Link in the description. Now, I want to improve this. These fractured points, they're flat. They're flatly sliced up. I want to add some noise in the interior sides of these fractured pieces. So let's go back up. Go back up to our fractured geo. Let's start off with selecting one piece, and we'll work on that one piece. And then afterwards we get it working, I'm going to apply it to all the pieces using a for loop. So let's just select this random piece. In order to manually select one fractured piece in the 3D viewport, click this cursor icon on the left side of the 3D viewport. Then on the top toolbar drop-down, select 3D connected geometry. Then left click a fractured piece on the model. Next, in order to isolate this piece, press tab on the keyboard while your mouse is hovering over the 3D viewport, and then type in blast. Delete non-selected. Now I want to add some noise to the green size, the interior primitives. But the first thing I need to do is add some resolution. There's barely any resolution other than the flat cuts that it has. I'm going to add a remesh. Cool, that adds a little bit more. I'm going to use adaptive because I want to keep the shape. That's a lot more resolution. I'm going to keep it at this level of resolution. Personally, I would make this a lot higher, but since I'm recording, I'm just going to keep the poly count a little lower. But if I was going to do this for like an animation, while I was not recording, if I'm not recording, I would make this a lot more higher topology. So maybe like something like this would be more desirable with more topology here. So it's a higher poly count. That way, the higher the poly count, the more details you can have with the noise of the interior. But since I'm recording, I'm just going to keep it a little lower. Actually, let me try and make this more. I will lower my point count. I'll lower my fractured points to like 50. So it's a lot less. I have a lot less points. Maybe that way can compensate. Oh, okay. Since I changed the point count, I have to manually select a different point. Now, if you remember correctly, this Voronoi fracture gives us an inside and outside group. So we know which side. That's how we colored the inside green. That's how we colored it. So I'm going to use that same group and add noise to the inside to make it look a little more interesting instead of a flat cut. Let's first split it. So we split the the inside and the outside. So this is our inside node. This is our outside. Now, if we think about this, our outside, we don't really need to change the exterior primitive. We don't even need all this topology on the exterior. We can keep it as it is because I'm not adding noise to the outside. I'm not adding noise to this side. I only need noise in the interior points. So there's no point in increasing the poly count for the exterior primitives. That's not going to be used at all. So I'm going to take this remesh and I'm gonna wiggle it out, move the split up. So now we have the inside. Oh, I should move this too. Okay, the inside. I just want to remesh the inside. So let's just do that. So now we have higher poly count here. So this is the original. This is the outside. And the outside is okay. Let's merge this together so we know what. So we have an idea of how it looks like. So the outside is nice low poly count. The inside has this high poly count. That's cool. That's what we want. Now I'm going to add some noise to this. Let's add a point jitter. This will move the points in random directions. No, that's way too much. So let's lower this scale. That's still too much. So that's 0. Still too much. 1. That's very, very subtle. That's a very subtle look. Let's go 5. Too much. 3. Now, this, I've tried playing around with the point jitter. It seems to go very extreme levels. The jittering is very subtle. So if you look at this at a far side, you're not going to be able to tell that there's noise inside. And this piece is very small. Like right now, we have this zoomed very closely. However, in the bigger picture, we have a lot of pre-factored pieces. So this is going to look very insignificant. And it might not even, the viewer might not even see this noise. So what I'd like to do is add a point VOP. And in the point VOP, I'm going to add some noise. So take the point, and I'm going to add noise to this. So let's take some noise. Let's try the flow noise. Okay, that's way too much noise. Let's lower this down a bit. Change this, select the A flow noise. Change this to 3D noise. It's way too much. So let's lower the frequency. There isn't much difference. Increase the amps. Okay, that's too much. That's kind of cool, but okay, that's moving it really out of shape. So I just wanted to see what it looks like before. So that's what it was before. It's moves out of place and out of shape completely. I'm gonna add a multiply. I'm gonna multiply the noise to make it a little, so I have more control over it. I'll multiply a constant to it. Now I only want the noise to move in a certain direction. I don't want it to get too out of place. Like I want it to stay somewhat in place, and I want the noise to be moving in the direction inwards or outwards and not all over the place, so it loses the complete shape. The perfect thing to use is the normals. The normals will point outwards, so you know the direction that the primitives are facing. So let's add some normals. Let's add some normals before we start adding the noise. So the normal node goes here before the noise. In the normals, I want to add it to the points. Okay, let's go back to the point VOP. I'm going to multiply. Now this is the normal. I'm going to multiply it here. Okay, it's way too powerful. Let me adjust this. It's a little better. Maybe adjust the noise a bit. That looks pretty nice. Maybe lower the rough. Okay, let's see what it looks without the template. It's still a little weak. I mean, we won't be able to tell far away. I mean, there's a bit of texturing you can see. Let's try this. Let's reverse the order of the point jitter and point VOP. When you're adding noise to this, you kind of have to try a lot of different. Okay, the point VOP isn't doing much actually. Let's make this 1 just to see what it looks like. It's kind of cool. I kind of like that. Turn up the frequency, flow. Okay, I'm just gonna leave it at that. You can play around with this a little more. So let's see what happens when we add the point jitter. Oh, that looks pretty nice. Very random. Okay, so after let's see what it looks like after we add the noise and we merge it. Now, as you can see, the noise is affecting the edges as well. So now we don't have this aligned anymore. These points are not aligned to the sides of the exterior surface. So we need to do something about that. Now, I'm gonna put down a point wrangle. We know where the exterior surface is. We know where these points are. Sorry, before I put down the point wrangle, basically we need to move these edge points back into place. We need to realign it back into place. But how do we get these edge points? First, we have to isolate the edges. Let's put down a group, create. I'm gonna call this seam line. And it's gonna be a bunch of points. And I don't want this. I don't want the base group. I would like to include the edges. Unshared edges. So all the edges on the outside, the outline of this piece of geometry is unshared. There we go. So as you can see, we have an outline. This is what we need, this outline. We need to realign all these points back to where it was originally, this So this will isolate it for us. Now I'm gonna put down a point wrangle. Now I'm just gonna, so we need to move the points. P. We actually need to move these points back into place. So P equals a new point. Well, first of all, I don't want to move all the points. So we have to limit our point wrangle to just the seams, the seam line points that we created from the group before. Only those ones, only the points in this group that we're going to be realigning. We're going to be modifying the position of these points, only these ones. So that's why we're going to limit this point wrangle to that seam line. Now, where do I want to move these points? Back to where it was. Well, how do I know where it was? Because now it's all displaced now. We have all this noise in here. It's all displaced. I don't know what the original position is. I've lost it. But we still have it here because it's still Houdini. It's still procedural. We never lose. It's non-destructive. The workflow is non-destructive. So if we go back up here in the remesh, we actually have the points here. Sorry, this is only for display. I'm not going to be using this node. Just wanted to show you we have the original position right here. We need to move it back into place in here. We need to move these points back to position to these positions. So let's put a null down. So this is the original P. That's what I'm going to call it. I'm going to plug this into the second input of this attribute wrangle. Put the render flag here. So for every point in the seam line, it needs to be repositioned. So every point in the seam line, let's look up the original point from the second input. Now, how do we look that up? We'll have to use a bit of vex. So there's a point function. Now, the point function takes 3 parameters. The first parameter asks us what input are you looking this up from? Well, this is Houdini is 0 index based. So this first input is 0. This is 1, and then 2, 3. So this one is the one that we want, which is 1. And what is the name of the attribute that we're looking up? It's P that we're looking up, the original P position. Now we need the point number. Well, the point number is the same. It's not like we added more points or we removed any points. Nothing was changed in this operation down here. Nothing was changed here. The remesh, this null is placed right after the remesh. Oh, we calculate the normals, which does not change poly count. This point fob does not change the poly count. All we did was reposition the points. The point jitter, the same thing. The noise is just repositioning it. Seam line, that just creates a group that doesn't modify the poly count at all. So we can just use the original point number. That's the current point number in the seam line. So we take all the points in the seam line and we reposition it to the original points here. So let's see what it looks like. Now it's hard to see right here, so I'm going to put a template here. Now you can see that this line is exactly where it was before. So let's merge this and let's see what happens. So this is what we get. Oh, let me get rid of the template. Now it looks like if you look carefully, the outline, the seam line is moved back and realigned to the exterior primitive. However, since our noise is too strong, it's overlapping. Some of the points from here is overlapping to the other side, to the exterior side. So it's not as pleasant. We'll fix that a little later. For now, I'm just going to stick with this. I added the noise to the interior for only one piece. Now this is the only piece that I'm working on. I want to add noise to all the pieces. And in order to do that, I'm going to use a for each loop. So I'm going to move this a little lower. So we know that this piece of code works for one piece. So all we have to do is apply this piece of code to all the pieces. So let's get rid of this blast. In fact, let's disconnect this as well. Let's get rid of the blast. From here, let's drag out a for each. Now I want to loop over each connected piece, each individually pre-fractured piece. So this is the one I want for each connected piece. The piece is here. Now I want to execute this split code. So I want to connect it here now. Okay. And this merge here is the output. So let me connect it to the end of the for each block. There we go. Now let me select the for each block. And it says merge each iteration. So it's going through every single piece and taking the result of that piece and outputting it at the end, because we have merged each iteration. If I chose feedback each iteration, that we're going to lose the previous iteration, and we're going to end up with just, that's like writing your name on a piece of paper and erasing it again 10 times. Then you only end up with one name on the piece of paper. But we want all the pieces. We want all 10 names if we're looping through it 10 times. Now this will take some time to cook when you put the render flag on the for each loop, because it's going through every single piece and doing the remesh, the noise, the outline, the realignment. Okay, it just finished cooking. So this is what we have right here. Let's add another exploded view to double check if it's working. So every piece has noise in the interior sides. Our noise is a little intense. We might have to lower down the intensity of the noise. But before I do that, I'm going to put down a file cache. Check the load from disk. I'm going to take out the hip name only because I have multiple versions of the file. But remember to take out the $F. Why? Because we're not caching every single frame. We only need one frame, the first frame. Because this is a static object, we only need to cache the object. We're going to move it around afterwards. Right now, at this point, the pre-fractured object is fixed in one position. So remember to remove the $F. This is important. Change valid frame range to current frame, because we only need one frame. And just save it to disk. I'm going to tweak the noise a little bit later. I want to get the whole simulation working first. I'm going to put down a null. So our pre-fractured object is now ready. Now remember, this is our pre-fractured geo here. This is the one that has the detail. This is the one with the edges bleeding out with noise. We'll tweak that a bit later. So there's actually one more thing I wanted to do. Now this pre-fractured piece, I'm going to add an exploded view here. This has quite a lot of points. It has 18,000 points. And it's not bad for my computer at this. The RBD simulation can be optimized by compressing the input geometry. That's our fractured geometry. In this scene, it's very unnecessary because the simple version of the input geometry has a very low poly count already, but I feel that it's important to demonstrate how to compress the input geometry before entering the RBD simulation. It's sending all the RBD object as it is, like this. We can actually compress. So there's something called assemble, which will take every single fractured piece and compress it. So right now we have 18,000 points. After the compression, we should be left off with a lot less points. So let's connect this first. Assemble. Geometry spreadsheet. Now in this assemble node, it says create name attribute. So that's this. So it's already identifying the pieces. However, each piece is still this is still 18,000 points. This is not compressing anything. We have to check this create packed geometry. What this will do, it will pack all the points belonging to each piece into one point. So let me just check this and I'll show you what I mean. So after I check this, my attributes disappear. Let's go to the points. And then the name, we only have 1 point for every piece. So let's take a look at the point count. We have 80 points. So we have 80 pieces. So let's scroll down. Yeah, we have 80 pieces because it's index 0 index. So it's 0 begins piece 0. So this is piece 79. So there's actually 80 pieces. So let's hook this up. I want to use this one because this is much more memory efficient. It's more performance wise. This is a lot better. Or actually, I'll just call it compression. Now I'm going to hook this up to this. To our out pre-fractured geo. No change so far. Let's go back to our simulation, see what happens. Now it's gone. We don't see our rubber toy. We don't see it at all. That's because we cannot use this RBD fractured object anymore. We have to use something else. It's called, just type RBD object. It'll list all the RBD objects here. This is the one we want. The RBD fractured object. Sorry, this is the one that we used before. RBD fractured object. The one that we want is the one below it. RBD packed object. The RBD packed object works by the RBD simulation needs to read it a little differently since we have the geometry packed together. It's all compressed together. So we can't just read it the same way that we did before. We have to use an RBD packed object. Like this. And so let's delete this RBD fractured object. We don't need it anymore. Now in the RBD packed object, it's very similar to the fractured object. We have a saw path, so let's connect that here. In the sim, okay, let me collapse this. In the sim context, I had imported the out fractured geo ahead of time into this, so it's easier to access. So let's choose this. There you go. Now let's just play it to see if it's still working. Okay, so it's still working. That's good. And let's go back to the fractured geo. So we have it compressed. That's good. Now let's see if this is still working. I'm going to connect the exploded view before the file cache. We have to connect it here. So because if we connect it to the file cache, it's pre-cache before I added the symbol, then we're not checking anything. We have to place the exploded view onto the end of the for each. Now that would be actually debugging something. Now, as you can see, we lost our interior noise. It's all gone. So let's go back up here. So somehow, by adding this compression here, has modified our noise. Our noise, our for each block noise. So we cannot have this here, but we need it to optimize the simulation. So what do? I'm just gonna move this aside. And I'm just going to connect this down here. So I'm going to bypass it. Okay, now it's cooking. So I'm just going to come back when it's done. Okay, it just finished cooking. Since I changed this this placement, I'm bypassing the compression. So the out pre-fractured geo. This is the simple version. This is still going to the simulation, to the .NET. However, I want to add noise to the interior size. So I'm faced with an issue. The assemble node that compresses the fractured pieces doesn't work with my noise generator. I can only have one or the other. Right now I have to update my cache. Now remember, this version here is not the packed version. This was never packed. We bypassed the compression here. So this is not packed. I'm gonna import the .NET. The simulation, I'm going to extract the simulation data where it falls down and breaks up that simulation data into this context first. So then we can replace the pieces with the more detailed one. So let's start there. Let's put down a DOP import node. This node will extract the simulation data from the RBD simulation. Now it's asking for a .NET network, so let's go. That's in the simulation. That's this .NET. Object mask. Well, let's go over there. Let's go over here. Select the .NET. go over here to the geometry spreadsheet. Now that's the RBD packed object. That's this that we need. Here, let's go RBD. You can actually just type RBD and just put an asterisk. It'll match whatever object like there. Fetch geometry, there we go. There we go. That's our geometry from extracted from the simulation. The goal at the end of the day is to replace these simple pieces cooked from the RBD simulation and swap it with our more detailed pieces with interior noise. This simulation to be using our more complex or detailed one, not this simple one. However, in the simulation, when we're doing the simulation, we don't really need the complex one. The complex pre-fractured detailed pieces, like the ones with the interior pieces. That one has a very large poly count, and it'll make it a nightmare to cook in the RBD simulation. What we want to do is simulate this one, this simple version. Simulate this one and replace pieces after the simulation is done, has been cooked, replace it with the more complex detailed pieces that we have created here. Now that's the goal. That's the more optimized way to do it. So there's a node called transform. Transform pieces node acts as a delay load for our RBD simulation, allowing us to cook the sim with the simple low poly count pieces, and then later on swap them with the more detailed noise pieces that have a higher poly count. This way it's more optimized. So it has 3 inputs. Now the first 2 are the only ones we need. The geometry to transform. And then we have template points. Now template points will be this will be the DOP import. That's our template points. This DOP import is fetching geometry from the .NET that has that compression. We had packed geometry. We had packed each piece of these geometries. So there's only 80 points and 80 pieces. This .NET right now, import style, it's fetch geometry from DOP import. It's getting it as is. It's not unpacking it for us at all. What I want to do is unpack it. When the DOP import node is set to fetch unpacked geometry from DOP network, this will extract all the data from the RBD simulation and unpack the geometry for us, resulting in the original 18,000 point count we had before the compression was applied. That was the original point count that we had before we packed it. So if I go here and I take a look, that's 18,000 points versus the 18 points after compression. If I extract the simulation like that, this will give us exactly what was unpacked. I'm gonna turn this back to fetch geometry from .NET and get the packed geometry, the compressed version from the sim. So we look here, the name is actually, if we scroll, here it is, the name is right here. So I'm gonna filter this, put name. So this is what we want. Now the transform pieces, this node, how does it know which piece from here? Okay, how does it know which piece from here to replace which piece from here? It'll know by the name attribute. So the transform piece, it says match by attribute, attribute by name. You can actually choose index. That should work too, since we didn't change the pieces much. But let's try this. So the DOP import right now, we have the 80 point. So this is our template points. Let's plug it into the middle input, the second input of the transform pieces, because it's asking for template points. So this is our points. This is our 80 points representing the 80 pieces because it's packed geometry. Hook this to the first one because that's the geometry we want to transform. Let's see what happens. Hey, that worked pretty well. However, I didn't even add a name yet. Oh, the primitive has the name. So this one already had a name left over from the Voronoi fracture. The Voronoi fracture node added a name attribute to the primitives of each piece in order to distinguish which primitives belong to which fractured piece. I'm gonna test this out. This is gonna take a little bit of time. Let me cook it first. I'm gonna go here. I'm gonna cook it first. Okay, let's go here. Let's go back up. Let's go to the fracture geo. Now let's go to the transform pieces. Oh, there it is. looks like it's working. Now let's, to test this even more, is to change this to the first frame, because if it's ever out of place, you'll know right away. Yep, that looks good. Because the transform pieces will swap each piece coming from the simulation for another higher poly count one. This is to speed up the cooking time for the simulation. This way you don't have to have a complex. It's harder to calculate the collisions for a complex geometry with the high poly compared to a geometry with low poly count. We cook it with our simple geometry, then we swap it out for a higher poly count geometry. Now of course we have to lower this noise level a bit. Put a null here. Now I'm going to lower the noise so it doesn't bleed out as much. Okay, it just finished cooking, so this is what it looks like. There's a lot less bleeding. However, there's still a bit of bleeding. Let me save it to the cache first. There we go. Now, the best thing about this transform piece is, I'm going to be a little lazy. I'm not going to keep tweaking this. Going back and forth tweaking this noise and recooking it takes a lot of time. And it goes back and forth. So I want to take a shortcut. And instead, now let's look at this. I'm going to swap the pieces out when it starts to crack. So to be honest, I can use these simple pieces at the beginning. There's no problem. There's nothing wrong with that because it hasn't cracked yet. Why would I use the detailed pieces? The only reason why I use the detailed pieces is because it starts to crack. I want to show the inside, the noise inside. So let's put the flag here and let's see when it starts to crack. Let's go through this timeline. Oh, there it is. So it starts to crack on frame 16. So 15 is fine. So 16 is the magic frame key. Now I'm going to add a switch here. You're probably going to know what I'm going to do. So I'm going to switch between this one and the transform pieces on frame 16. I'm only going to use the transform pieces starting at frame 16. That way the bleeding won't look as noticeable. So let's plug this both in. Put the switch here. Plug this to the out. We need a way to toggle this switch, the switch to this transform piece on frame 16. So we can use an if statement. So we use an if. So the current frame equals, actually, greater than or equal to 16. It would be true. What would we want the number to be true? So when it satisfies, when the frame is 16 or above, I want it to be input 1, then input 0. So what this is saying is for all frames 16 and greater, we're gonna use input 1. So that's this input, the complex, the detailed fractures. All other ones, we're going to use input 0, which is this one over here. This one. So let's see if this works. Put the render flag here and let's play a few frames. Okay, so these frames I can't tell, but let's highlight this and go like highlight the switch node. Click the select input. So it is using input 0, which is this one. So good. This should be working fine then. And you can also tell by it loads a lot faster for these ones too. For the next video, I plan to do another Vellum tutorial that builds upon the previous Vellum for Beginner video. I wanted to set up a Vellum sim that would interact with some RBD objects. That was one of the main reasons I needed to record a destruction tutorial video before going ahead with the Vellum interaction tutorial. Please stay tuned. I'm hoping to get that out in the next week or so. Thanks for watching and sticking to the end.